Okay, so if we continue here with the second problem, we see that we have a subtraction problem in scientific notation. So what we're going to have to do here, if you recall, is we're going to have to line up our decimals, which means that we have to change one of these exponents so that it's the same as the other one. I typically will change the smaller exponent so that it's larger. It tends to work out a little bit better that way. So we'll see what happens here. So we have a 9 right here. Oops. Oops. Okay, so we have a 9 right here, and we have a 7 right here. What I'm going to do is I'm going to change this to a 9. All right, so if I change this exponent to a 9, it becomes 2 powers of 10 larger, which means that, boom, boom, my coefficient must become 2 powers of 10 smaller. Okay, so when you add that up, you're going to get something like 4.40128, and then it's going to be times 10 to the 9th power. Well, the good news is that this is in the proper scientific notation, so we don't have to mess with the decimal and the exponent. The other part of this is, so this is where we really start having to think, because remember when we add and subtract, we look at the least precise value going into the problem. And when we have that least precise value, that's going to limit our answer by places, not by the amount of significant figures. You can only evaluate those places, though, when your exponents are both the same. So you have to wait for a minute to evaluate this. So if I add this up, I get this calculator answer. My first measurement goes to 1, 2, 3, 4, 5 places after the decimal. And my second measurement goes to 1, 2, 3, 4 places after the decimal, which means that oops, not there, this is my limit. So I end up with 4.4013, sorry, I scribbled that out, I wasn't counting properly, times 10 to the 9th kilograms. Okay, so you got to watch those significant figures. It's not just about cranking out the math, it's about using the correct amount of significant figures and thinking scientifically. And again, I think you probably believe us by now, but we're going to be doing this the rest of the year, so you have to figure out how to do it, okay? Okay, so we have Josie and Bill here, and they were in lab, and they produced 4.84 grams of oxygen gas, and that was through a decomposition reaction. So they drove off this much oxygen. Now, theoretically, with what they started out with, they should have been able to produce 5.37 grams of oxygen. Okay, so here's the key word, should have produced. And we want to find out what the percent error is. So the first thing that we're going to need is we're going to need to have a basic equation. So percent error is equal to the absolute value of the theoretical yield minus the actual yield. And those two things can be reversed because you're always taking the absolute value. And that's going to be divided by the theoretical yield. And then that's going to be multiplied by 100. Okay? That's going to give you your percent error. So your theoretical yield is 5.37 grams. Your actual yield is 4.84 grams. And we take the absolute value, of course that's going to be positive, so it won't matter. And then we're going to divide that by 5.37 grams and then multiply by 100. Okay, so you're going to answer this in 3 significant figures, because that's what we're starting out with everywhere, 3 significant figures. And it looks to me like, if I remember properly, this is somewhere, it's going to be around 9 point something percent. I'm not exactly sure, but just make sure that you subtract and then you divide by this 5.37 and then you multiply by 100. Okay, so 3 significant figures, and that's all there is to that problem, and you will have to know that equation. Okay, Antonio, his faucet was dripping and he should have fixed it, but at a rate of 45 milliliters each hour. Okay, that's a lot. How many liters of water are wasted each week? Okay, so this is dimensional analysis, and you're going to have to solve a problem like this on the written portion of your test. So what do we know? We know that the drip rate is 45 milliliters per hour. Now don't put your hour as a side fraction because it won't be as easy to solve. Now, our first job is to get milliliters to liters. And our second job is to get hours to weeks. So let's work from the top first and go to liters, since this is probably the easiest thing. So we put milliliters down here. We want to get rid of it. We put liters up there, and that's the unit we want to find. So liters are bigger, put a 1 there. There's 1,000 milliliters in a liter. Okay, now that I'm almost there, except for now I have to go from hours to weeks. So we're going to have to just use some time conversion factors. And we want to get rid of hours, so we put this up here. I do not know off the top of my head how many hours are in a week, so I'm going to put hours per day. So a day is bigger. 1 day, 24 hours. I now have gotten rid of hours. So I don't want days, I want weeks. So I have to get rid of days, and I want to get to weeks. All right, so what's bigger? A week. How many days in a week? 7. All right, so that helps me to get rid of days. And if you look where I am here, I have liters per week. All right, so you're going to multiply 45 times 24 times 7, and then you're going to divide it by 1,000. And I think it's, well, let me just crank it out real quick here so we can look. 45 times 24 times 7 divided by 1,000. Is that right? Let me do it again. 45 times 24 times 7 divided by 1,000. Much better. Okay, so I have, if my math is correct, I've got approximately 7.56 liters per week. And the reason I say wasted is because you can really increase your water bill by not fixing your leaky faucets. Okay. So if the math is wrong, please forgive me. I'm working rather quickly here. Okay, let's go on to the next problem. I'm going to skip 10 evidently. We're now looking at average atomic mass. And what you're going to have to do here is read the problem carefully, and you're going to have to link together the things that go together. Okay, so what you see here is if you have a B11 isotope, that it's going to have an average atomic, or excuse me, it's going to have the mass of 11.01 atomic mass units. Okay, so these two things here are connected. And then if we have about 20% of this B10 isotope, that's going to have a mass of 10 AMUs. All right, so you'll recall the way that we set this up is we multiply the percentage by the mass, we add it to the second percentage times the mass, and then we divide by 100 to get a percent. So we've got 80.20%, and just label everything. All right, and we are going to multiply that by 11.01 AMUs, and we'll stay with AMUs. You could go to grams if you want. Now, that product is then going to be added to the product of the second percentage multiplied by the mass of that specific isotope. Okay, and then you take the whole thing and you divide it by 100, and that's going to give you your average atomic mass. I'm not going to do this calculation, but I would like to point out to you that it's really necessary for you to look at this 11 and look at this 10 and to know that your average has to be somewhere between these two values. All right, so since you have more of the boron 11 isotope, you're going to end up with something that's approximately 10.8 as far as your average atomic mass. So since we're using percentages to the hundredths place, you want to go to the hundredths place. So make sure that your answer is going to make sense. Now, I really don't know exactly what it's going to be. There's going to be one more significant figure here, and that's going to be average atomic mass, AMUs, which would also translate to grams or grams per mole. Okay, conversion, the mole principle. 75.3 grams of calcium, and we want to go to moles. Okay, so this is fairly straightforward here, nothing tricky about it. Here's your given, 75.3 grams of calcium. And since we're going to be converting it to moles, we have to put grams on the bottom and moles on the top. So remember, 1 mole of a substance is equal to the molar mass of the substance, all right? In a conversion factor, we always put a 1 next to moles. And then if we have a mass, we have to look at our periodic table. And then we're always going to round to the 10th place. And so what we would do is we'd go ahead, whoops, that's an equal sign. We'd go ahead, we multiply across, and then we divide by 40.1, so you can see that it's going to be 1 point something something. Now, why do I say that I have something something? Well, I'm always going to go back to my given for my correct amount of significant figures. Okay, now what's my unit? Moles. Okay, so go ahead and crank that out on your own. You should be able to come up with an answer. How do I know it's 1? Well, 75 divided by 40. I know it's going to go in 1 time and some more. Okay, so I just estimated it so that when I actually would crank out my answer, I would get something that would be agreeable with what I thought. Okay, now sorry about not cranking these out once again because I left it at school and I don't want to redo it. Okay, on to the next question. Atoms in 9.44 grams of gold. Okay, so now we're finding atoms and we have a mass. So 9.44 grams of gold AU. Give me my gold back. And we are going to atoms. So grams of gold have to go on the bottom and atoms of gold go on the top. Now, number, unit, substance, number, unit, substance, number, unit, substance. So here's where I have to think about this for a little bit. I think I told you to do this in 2 conversion factors, so I'll do it in 1 first and then I'll do it in 2. As far as my grams, I think it's 197.0 grams of gold for every mole. And then whenever I have atoms in my conversion factor, I'm always going to put Avogadro's number there. Okay. Now, since we're talking about atoms, we would expect to get a very large answer. All right. Now, this value here, 9.44 grams, if this is the molar mass of gold, this is actually going to be an answer that is going to be proportional. You will have less atoms than Avogadro's number. Okay, how many significant figures? You're going to have 3. Okay, and I bet your exponent is going to be times 10 to the 22nd. Now, if you are asked to use 2 conversion factors, all you do is this. You would say, I have to get rid of this, grams, and I'm going to go to moles. And then all you do is go from moles to atoms. Okay, so all you're doing is you're using moles as a bridge, which is fine. It's not necessary that you do it this way. I just want to make sure that you understand that you can do it this way. So again, it still works out to be the same thing. Okay, the takeaway here, you must know, of course, that the molar mass of a substance, is going to be equal to Avogadro's number of particles, and that's going to be equal to 1 mole of whatever we're talking about. So you need to know the equalities. Okay, so this one may be a little bit more difficult, not a whole lot. So we have a penny now, and you know that in pennies we have zinc in the middle and they're surrounded by a little bit of copper. So we have this many atoms, all right, this many atoms, shoot, okay, yeah, we still have this many atoms, and we want to know how many grams that is. Okay, 2 conversion factors. 3.12. I always start out with what I know, times 10 to the 22nd atoms of zinc. And then I have to use 2 conversion factors, so I can go ahead and set them up now. All right. I want to use 2 conversion factors, so as I did in the last problem, I want to go from atoms to moles. Okay. And we're talking about zinc here. And then I want to go from moles to grams of zinc. Okay, now in a conversion factor we always put a 1 next to moles, and we always put the molar mass next to grams, and I'm guessing that it's 65.4 grams. I am not positive. And then atoms in a conversion factor is always Avogadro's number. Okay, so if you do the math here, what you can see